Hello all, and welcome back to our Lunch and Learn series. I'm Heather, taking over for Thomas this week, and today we are fortunate to have Michael Anger joining us. Michael is the founder and CTO of Unisphere. And just a quick, this is our final wrap-up series from the series this week, and I will hand it over to you, Michael. Thank you.
Thank you, Heather, and I'm briefly sharing my screen. So waiting a second before I start, and I'm very pleased to be speaking here. Thank you, Heather and AVL team, for giving me this opportunity. I'd like to talk about digital twins and road simulation for electric aircraft operations from our side. My name is Michael Enger, as Heather said, CTO and founder of Unisphere. Unisphere is a small company, startup based in southern Germany, and I'm happy to talk to you today. We have a Q&A session at the end of this one, so if you ever have questions, please share them in the chats. We will discuss them, select and discuss them later. So a little snapshot about Unisphere. Unisphere is a startup in southern Germany, founded in 2017. We are about a team of 20 people, all aviation passionates and software engineers, and myself being an engineer in aeronautics and working for quite some time in flight testing. So we are operators at heart, and today we support companies, operators, flight operations all around the world with software tools and tooling for analytics, but also actual flight operations. At all altitudes, so to say. So we are active in the stratosphere for high altitude pseudo satellites. We have projects around there. Then the more new innovative air mobility segment of air taxis and eVTOLs. The drone space is the main space we are active in these days with software tooling and some infrastructure projects. So to say, we are passionate, and the whole team is aviation enthusiasts. So we have also a long-standing history in that space, and we originate out of the Solar Impulse project. I'm not sure if one of you guys have heard about that project. So it was the first solar-powered airplane flying around the world in 2015 and 2016, purely solar-powered, as mentioned, and it was basically giving the starting point for electrified aviation as we know it today. But this is 10 years ago, but there's still a lot in common of what we do today. So for example, the solar powered aircraft at that time was flying very slowly with about 25 knots indicated airspeed, had the weight of a mid-sized car and the power of a scooter. So you can imagine that flight planning in these days was very, very challenging, especially as the flight was some legs of this flight around the world were quite long, and the longest flight was from Nagoya in Japan to Hawaii in a 5-day and 5-night flight, continuous by one pilot. And I'd like to show you a little bit what we did at that time and what we do today, and how our collaboration with AVL looks like today. So in a few seconds, a black screen should arrive on your sides of the screen. So, and you will be seeing a moving dot taking its path from the very left, a flight from New York to Sevilla in Spain. And the data you are seeing is actually weather data forecasting the flight of the dot in the middle, the aircraft, in a 3.5-day flight. At that time, it was our task basically to develop the simulation environment to find out the best flight trajectory for this aircraft. And the black areas you see are blue sky areas. So remember, it was a solar powered aircraft, so it was flying only under blue sky conditions. And during nighttime, we had to take out the energy of the batteries. So it all brought together like flight trajectory prediction, performance modeling of the whole powertrain, and sensitivity to weather at all. And then certainly the decision to go or not go, which is a very singular event, right? Before the flight, you decide to take off or not. And Today, there's a paradigm shift in the aviation and aeronautics industry happening right in front of us. Some of you might already be in touch with one or the other drone company in your area. So we see drones doing surveillance mission, doing long distance deliveries for cargo to oil platforms, oil rigs, or wind parks offshore, or some examples from the US, like Google Wing is flying 3,000 deliveries per day or over a weekend in Dallas and some other cities. Or Manna from Ireland just started a drone business in Tulsa, aiming for 2 million deliveries this year. So there's electrification everywhere in the drone space. And what's happening as well in parallel is electrification in the eVTOL world. eVTOL stands for electrical vertical takeoff and landing. So meaning kind of a helicopter, just a bit more quiet, less parts, less moving parts and so on. So more efficient in their daily operation. That's happening. So you have operators, OEMs like Joby working on the certification and the first flights, doing a lot of flight testing these days. And midterms, we will see some of the conventional aircraft being more and more electrified and transporting more and more people. So all of these electrified aircraft have some similar challenges, some more strong than others, but certainly new challenges with the rise of electrification in the aerospace world. So one is certainly the uncertainty in range. The wind impact is quite significant. Imagine you have tailwind or headwind component on your flight, which makes the energy demand unpredictable, or at least hard to predict from a day-to-day basis or even during a day. Then the batteries are sensitive and degrade over time. So how much actual state of charge and how healthy is your battery is also something you need to monitor over the whole life cycle of a flight operation. Then if you're an operator, you want to put a network of connections from city to city. So you need to kind of find out what's the best aircraft for a certain route, and how does this route and flight duration change over the season due to the different wind impacts or outside air temperature impacts. And then certainly, as always, cost pressure of airline operators. The promise is electrification is more simple to operate and cheaper in the end, but that's a promise. You as an OEM, as a designer, you have to really do and prove in daily operations. So on our side at Unisphere, we like to approach this topic by creating virtual twins of flight. So we do large-scale simulations of flight trajectories. So we are able to simulate a flight before it happens. And we can tell exactly what the weather should be, at what altitude and what time. We can tell you about the actual flight duration or where the aircraft should be at what time and altitude. And for this, we do integrate aircraft performance models from a very simple way or a very sophisticated model that we actually really do simulate the flight dynamics, so acceleration, deceleration, climbs, descent, and so on. And we have a service availability of high resolution weather data all around the world. All that together will basically create a virtual twin of flight. And the second part on this slide is more about evaluating this data set. So as I said before, is it a go or no-go decision, for example? That's something you want to get out if you want to automate things. Now, with this data set, you can do two things. You can either use it in live operations to tell if a flight is go or no-go based on the energy, for example, or the weather conditions, or you can use the same technology with historic weather data and do studies. And I brought two examples. One is a service uptime prediction. Imagine you're an airline operator and you want to know how often can I fly this or that route at Tampa Airport. And then you can give your parameters, your operational parameters, some limitations where you say it's nominal, moderate, or severe. And in this output, where we looked at 3 years of weather data, 5 years of weather data on an hourly basis, you can already see the condition change over the course of a year from nominal to more moderate conditions during the summertime, and to more nominal conditions during the winter time. If you are now an OEM, you can also look into the more details of what are causing these moderate conditions, for example. And that's why what the second graph is helpful for. So you see the gust factor line in purple or pink, being the main reason for the moderate conditions, why this is happening over the course of the year. And so you can design a more wind resistant aircraft, for example. Another example and a challenge for the eVTOL industry, so the air taxi industry, is icing conditions. So if you look at, for example, Calgary over the course of a year, you have a very high chance in the wintertime that you have icing conditions, which is here more red, and during summertime you have no icing conditions. So as a manufacturer, you should plan for that. Basically, you need to equip your aircraft with a de-icing system. Whereas if you're going to operate in Atlanta, further at the bottom, you see that icing conditions is not so much a problem for daily operations throughout the year. So you can play with different configuration of your aircraft already at a design stage with this digital twins of a flight. Now, talking about our collaboration with AVL, we were wondering how we could combine the worlds of very detailed modeling in AVL Cruise M and the Unisphere flight trajectory world. So we were asking about the questions: what could we do if we could replay a mission before flying it? So we could create actual mission profiles like the real users would have, and then derive power demand and load profiles for testing engines or motors or batteries and so on, the whole powertrain. Or if the question would be like, what if the thermal behavior is different in a region like Dubai compared to something in New York? So is there different sizing required of the insulation? And what if we could do all that in a reproducible and highly scalable way? So what we did over the last months was we basically connected both worlds of the Unisphere digital twin of a flight with the AVL Cruise M product to basically talk to each other and have a very detailed powertrain model running in the AVL environment, then asking for the flight trajectory information, so power required for a certain flight phase or operating conditions, environmental conditions, so that the user in the AVL environment could basically benefit from real world data. With a partner from the US, from Blue Flight, we were building a model that was the AVL part. So AVL built a powertrain model and then validated it against actual telemetry data, which are the two graphs below. I wouldn't go into detail right now. But model building is something AVL is specialized for. So that's what they did in the first place. And then we rerun that model with the flight trajectory prediction on 4 different locations. So this is a case study now on 4 different locations, but all equal flight distance, all equal vertical profile, and 3 years of data and hourly flights, kind of, which created 76,000 data sets of virtual twins of flights and cumulated like 29,000 hours of flight just within about 20 minutes. So that's really performant. And with this data set, you can now do further analysis. Now, results. So certainly I can only give you a snapshot here, but one is interesting about the thermal behavior of batteries across location and years. And here for this case, I selected Dubai as part of the output of this study. And if you look at the top graph, you see this red charts with the temperature distribution over the course of a day through 3 years. You see there's quite high outside air temperatures ranging up to even 65 degrees centigrade, but the majority is about 50 degrees of centigrade. Whereas, for example, for San Francisco, just below, it's a bit lower, or even New York is even lower. Now, this is not surprising, but if you look at the second graph at the bottom, you see the data staggered over 3 years, year 1, year 2, year 3. And interestingly, the green curve is what I like you to eyes point at, is that you see a cell temperature rise. So the temperature during a flight rising within a battery cell of the drone completely varies over the course of a year. And surprisingly, it's New York and not Dubai. Why is it New York? If you look at the course of a year, you see the high temperature rise of a battery cell in the winter times in New York and not in the summer times. This is due to the higher outside air temperature. Sorry, due to the lower outside air temperature in New York during winter times, which increases the inner resistance of the battery and therefore increasing the heat created in the battery during a flight. So a cell during a flight would heat up by about 35 degrees centigrade during winter time, which is quite significant for the operating range of batteries. And therefore, you can already give a feedback loop to the design team on talking about battery cooling or battery heating or insulation mechanisms. Here's another example. Here it's more about a seasonal effect on battery state of charge. So what you see in this plot is the distance of a flight and the battery state of charge along that flight path. And this for different seasons of the year. And what is interesting here, and with the effects explained earlier, is that the battery state of charge for the same route, same distance, same drone, same battery, varies over about 15% state of charge, just due to the different environmental conditions, mainly outside air temperature here, for the same flight, which is quite something interesting to do the battery sizing or even exchange different batteries during the course of the year to gain more payload throughout the year. Now some takeaways. What we proved with the AVL collaboration is that AVL makes it now very very easy to explore different operational conditions virtually, which are really mimicking the real world conditions. So we can do that in a reproducible and scalable way, and you can start to do a lot of variant testing. And this certainly helps to reduce the number of flight tests you have to do, but it also supports the documentation required in the aviation for design and verification processes. One point I already mentioned is like you can already assess in an early stage about your energy and thermal margins. If it's worthwhile to do a modular design where you on one hand have an insulation, on one hand not, or you play with the different cell sizing and packaging mechanisms you have. So this can be explored already beforehand. With the modeling part on the AVL side, you have also a very distinctive model where you can find a good reason for the root cause of a certain effect and can play just on this little element, let's say the insulation of a battery, the thickness, for example, just by changing that, rerun the simulation, see the effects with real world conditions. And the scalability certainly is a big factor because we can help you and AVL can help you to do that at a large scale and throughout in all places around the world. So you can compare different designs of your system in different parts of the world and then take the decisions whether it be a single solution or a modular solution for your product. And last but not least, when we talk to the airline operators of the future, and here I mean really like the drone operators of the future, the eVTOL operators of the future, they are aware of these problems and they ask for solutions because they want to have a cost competitive aircraft which lasts longer than 1 year. So they ask about state of health, they ask about state of charge and the overall life cycle, how it would behave in the real world conditions. And with that, I'd like to already come to an end with my presentations. I'm also here for furthermore questions, and thank you for listening in.
Thank you, Michael. That was very interesting. That was surprising to see that there's such a difference in state of charge between, saying, flying the same flight path in June versus December. So it's much more than just as you mentioned, it's like super important for the go, no-go flight. That's probably the most important question that you answer. But it also sounds like it changes quite drastically during the day. So in the morning, your flight path could look quite different yesterday versus today.
That's correct. Especially the temperature is one thing. Now operators already do some preheating or preconditioning of their batteries, but there's also, it's not just about temperature, it's also about wind conditions. So you have changing wind conditions over the course of a day. If you live close to a seashore, you know exactly about the diurnal behavior of seashore wind and landshore wind conditions. So that changes your flight time, and your flight time changes the minimum state of charge and all this. So you can study a lot of different effects in a high resolution, with high resolution, with real world weather data, not just like the average temperature of a location. No, it's really like, how would it operationally look like if I want to fly in the early morning hours, and does it differ if it's midday? And you want to get that certainty because in aviation, the safety is still at utmost, it's the highest conditions. So regulators ask you as an operator for this information, and the operator will ask the OEMs about these questions.
And so then this is probably a naive question. How predictable is the weather? It seems like, especially more and more, it becomes less and less predictable. So how drastically would the flight path change that you submit to,
Yeah, good question. In the end, all around the world, the different companies and weather services are working on more higher resolution and higher update rate models, which is great. But in the end, as an operator, you need to decide on a certain information basis you get to just before takeoff, and that's why we also have these services in place where you send us a route, we do the whole route check for you, and you get the no-go or go decision, certainly with your limitations. We are not doing the weather information, we are consumers of weather information, but there's a huge invest into that industry to deliver high fidelity modeling in the weather prediction part as well. So that's more real life operations.
Very cool. So that brings me to a more fun question. Back to your solar flight, what sort of that was going around the entire world. What sort of unforeseen challenges kind of came up that changed your plan or resulted in hard decisions? And was there ever a moment that was like, yeah, we'll try this? Or you have to be pretty confident, I would imagine, in your models.
Yeah, hard question, and too many memories to tell all of them in once, but we were not gambling with that flight around the world, so we had to rely and have to build up a good decision pipeline, how to come up with a decision before the flight. That's the hardest. And then in aviation, there's always this point of no return. And actually, there are some documentaries out there on YouTube about your solar impulse crossing this point of no return. And certainly, when you're in flight, you get new weather updates, you get feedback from the pilot, you get feedback from the model, so you keep continuously updating your information you're basing your decision on. And certainly, yes, there were hard decisions, and each flight was hard to decide to go or no go. So I can't tell a specific example right now. But check out the documentaries there. It's really interesting.
I will definitely have to check out the documentary, especially crossing the ocean. As you mentioned, it's as a solo flight, a solo pilot, multiple days. There's no safety net, right? It's not like there's another plane like ready to, if there's an issue in mid-flight, right?
Yeah. So, well, we had built some safety nets. Certainly, the most fragile, let's say, was kind of the aircraft itself because it was new. And that's our daily business now. eVTOLs are new. It's electrified. It's all new. And all the engineers, all the regulators need to build up experience by testing, by simulations. So we had safety nets, and the pilot had a rescue boat and so on. But still, we never wanted to bail out. Certainly, while flying. Um, which brings me to the next project there, because there's already another project like that in the pipeline, and it's called Climate Impulse, and it's a non-stop flight around the world with hydrogen power only. So it's gonna be, we are involved in that as well. We just did an announcement recently, but that's gonna be a similar experience, hopefully in the near future.
Oh, that's super exciting. So do you foresee, I have a lot of questions on that, but do you foresee solar panels on future aircrafts, or are we going to rely solely on batteries and or hybrid?
I would say solar cells are not the game changer there. They were helping for solar impulse certainly, but game changers are higher battery densities and hydrogen power. And what's happening now in the drone industry since a few years, I would say 1 to 3 years from now, is hybridization. So a combination of combustion engines with electrification, with batteries as buffers or storage of energy. And this is challenging for the most of these robotic companies because it's a very complex system you're building. Combustion is like the hybrid cars, so that's why companies like AVL exist, and that's going to be a challenge in the next years for these manufacturers to build the right systems. All the propulsion chain needs to be well thought through.
Yes, there's lots of trade-offs in systems that. So for your next project, when you say hydrogen, you're speaking of fuel cells, right?
Exactly, it's
Or
liquid
yeah,
hydrogen and fuel cells. So
liquid cell.
yeah.
Very cool. Um, that's cool. So liquid hydrogen, hybridized with batteries and to make a full loop around the world.
Exactly. That's one of the
With that,
projects we are working on, and
yeah.
maybe also AVL will become a partner in that. We'll see. But certainly we need some knowledge and power and simulation environment to actually get this done.
Yes, I can I can only imagine. So coming back to just we have a couple minutes left. What in the earlier time frame, what challenges will we see with drones and air taxi companies in just the recent years, and why is AVL's expertise? I mean, I guess we've touched on this a little bit, but if you could expand a
Well,
bit more on
that's
more
fine. I think
current.
one part I mentioned is like really like the hybridization is a key challenge I see, where the capabilities of AVL will be of great help. But I also see that AVL has to learn a lot about aviation in its actual. I mean, AVL was an automotive company. Now it's changing. There's a trend going on, which I like, because now we can benefit of all these experiences made in the automotive industry, and the aviation industry needs to learn a lot about this hybrid configurations, but not solely. It's also about battery modeling, battery state of health. I mentioned in the presentation. So the state of health questions is fundamental because it's the cost driver of drone operations. If you imagine a drone system is the cost of a drone system, 50% of that is about the battery, and it's and if you fly very often, you quickly get a lot of cycles on these batteries, so you need to exchange the batteries. So each percent you save in this dimensioning, in like handling the batteries in a daily flights, will help to make this more efficient and make the economics work.
Oh yeah, that makes sense. There's a lot of working knobs to tune. Last quick question, what's the benefit of why would someone take an air taxi over a helicopter?
It will
Just
be long term. I think it will be cheaper. I cannot tell how much cheaper, but if you look at the same for electric cars, I have one as well, so it's a lot cheaper than taking a gasoline engine, a normal combustion engine. So I think long term the competitive advantage is really about less noise, and cheaper operating costs, less moving parts, and so on.
Oh, very cool. That makes sense. Okay, we've come to the end. I will stop myself because I could keep going. I greatly appreciate your time and sharing your story with us, and we will definitely be looking forward to your next project.
Thank you for having me, and all the best to you all. Bye.